Good afternoon, everybody. Lecture number 11 in the course on laser matter interaction. And today I would like to continue to talk about quantum mechanical description of laser matter interaction, in particular about application of the concept of density matrix for the description of time-resolved experiments. Well, we were talking last lecture about density matrix, and today I would like to emphasize that every element of density matrix has clear physical sense. And in order to explain this, today I would like to introduce new concept of Bloch sphere, and with the help of Bloch sphere I would like to explain you two very interesting phenomena which are called spin echo, or something very similar to this, photon echo. But let me start from the very beginning and remind you what we were doing last lecture. Last lecture we were trying to develop an approach for description of laser matter interaction where matter was modeled as an ensemble of two-level systems and light was still an electromagnetic wave. So sinusoidal function of electric field was representing light. So what we did, we tried to find solution of time-dependent Schrödinger equation, and we were looking for this solution using perturbation theory. And in perturbation theory we were searching for solution of the wave equation, and solution is a wave function psi, and this wave function psi was represented as a linear combination of two wave functions and the phi1 and phi2, and these two wave functions are solutions of stationary Schrödinger equation. So these two wave functions phi1 and phi2 are were the functions of coordinates only. And since the total solution should be solution of a time-dependent Schrödinger equation, so we must introduce also dependence on time, and dependence on time will sit in these two coefficients, C1 and C2, these two coefficients in front of these two wave functions, in front of these two solutions of stationary Schrödinger equation. Then we were introducing, the last lecture, we were busy with introducing of the density matrix, and I showed that the density matrix can be written as a product of the coefficients C1 and C2, so different combinations of these coefficients will give me different components of the density matrix, and this way the diagonal components of the density matrix were given by the product of C1 complex conjugate C1, and this product should be averaged over the ensemble of two-level systems, and for another diagonal component we will have product of two other coefficients, C2 star, C2 complex conjugate, and C2, and it again should be averaged over the ensemble of two-level systems. So this from here you can see that diagonal element of the density matrix basically represents the probability to find the electron either in state 1 or probability to find the electron in the state 2. But what about off-diagonal components? So off-diagonal components, this is more interesting issue if you talk about quantum mechanical description of light-matter interaction, and if you talk about density matrix in this particular case. So off-diagonal components will give us dipole moment, average dipole moment of the ensemble of two-level systems. If you want to see it better, what you have to do, you have to write the expression for the dipole moment averaged over the ensemble, as I showed last lecture. If you want to calculate expectation value of whatever quantity you are interested in, so you calculate this expectation value using the density matrix, an operator of this quantity that you want to calculate. And in this particular case, if you are talking about dipole momentum, then this the operator of dipole momentum will be written in this form. And if you then calculate the sum, you will see that the off-diagonal components of the density matrix times the result of this integration d21 and d12. So then this eventually this sum will give me the dipole moment averaged over the whole ensemble. And dipole moment averaged over the whole ensemble times concentration of the two-level systems, and the ensemble will give me total polarization. So basically looking at this expression, you can say that off-diagonal elements of the density matrix are practically related to the total polarization of the ensemble of two-level systems which this density matrix describes. Well, now let's be more specific. So we have ensemble of two-level systems, and we were, well, initially each of these two-level systems is described by this by the wave function with coefficients C1 and C2. If you talk about the whole ensemble will be described by the density matrix with 4 elements, and the elements of the density matrix, as we discussed already, would be given by these products. So diagonal elements and off-diagonal elements. As I said already, diagonal elements will describe the probability to find electron in the ground state, probability to find electron in the excited state, and you can see also here that rho 1, 2 and rho 2, 1 are basically complex conjugate with respect to another. So rho 1, 2, for instance, is a complex conjugate of rho 2, 1. And looking at this, you can again write the expression for the dipole moment averaged over the whole ensemble, and again confirmation of this, of the things I have told you already, that if you talk about the off-diagonal components of the density matrix, it practically tells you something about dipole moment averaged over the whole ensemble. So now we have ensemble of two-level systems. In each of these two-level systems we have a specific, some wave function, some coefficients C1 and C2. They will be different. So as you can see here, if for one two-level system coefficients C1 and C2 have one time dependence, then for another two-level system they may have different time dependence, and then for the third two-level system they may have even third type of time dependence. What density matrix tells us is the product of C1 star times C1 averaged over the whole ensemble, and C1 star C2 averaged over the whole ensemble. So averaging over the ensemble is important when you talk about density matrix. Otherwise, if you don't do this averaging, there is no point to introduce density matrix. You can simply work with a wave function. So then introduction of density matrix is the reason for introduction of the density matrix is do this averaging. So you can also say that density matrix is practically a result of merging quantum mechanics and statistical physics. Well, now let's try to introduce a very simple concept which is called Bloch sphere, and the Bloch sphere will help us to understand such phenomena as spin echo and photon echo. So Bloch sphere is nothing else but a way, an intuitive way to represent a wave function of a single two-level system. So if you have a superposition of superposition of two states, if you have linear combination of two wave functions phi 1 and phi 2, and this linear combination depends on time, and the sum gives me the solution of time-dependent Schrödinger equation psi. What I do now, I express a part of this time dependence explicitly, and this time dependence would be, of course, for a single two-level system, will have to contain frequency omega 1 such that h omega 1 will give me the energy of the ground state, and h omega 2 will give me the energy of the excited state. So this time dependence I will express explicitly in these wave functions, and these coefficients corresponding to the wave functions. And what is very important here, that I also introduce a phase delay between C1 and C2, and this phase delay is given by this parameter phi here. Then each of the coefficients has the amplitudes, has time dependence, and it has some phase. So then after that you can express this expression, you can write this equation slightly differently, where, as I said, you express this time dependence explicitly. So the time dependence will be seen as oscillations at frequency omega 1, oscillations at frequency omega 2. And these two frequencies once again correspond to the energies of the ground and the excited states. And what I can see now, that this function psi can be expressed with just two parameters, theta and phi. So basically, in order to show that only these two parameters play the role in the main role in the definition of the wave function psi, we can even plot this wave function using a sphere where this theta and phi will be given by two angles, and the wave function in this case will be expressed just a vector on this Bloch sphere. So this sphere is called Bloch sphere, as I have just said, and the idea of the Bloch sphere is to show these two parameters, once again theta and phi. And after that, the description becomes very intuitive. So basically, every wave function will be represented by a vector on this Bloch sphere, and for every wave function, for instance, for every vector, you will be able to say what is the probability to find the electron in the ground state, what is the probability to find the electron in the excited state. So this is the ground state, this is excited state, or the other way around, it doesn't matter that much. And now it's very interesting to talk about ensembles of two-level systems using the concept of Bloch sphere. So if you talk about ensemble of two-level systems, for each two-level system in this ensemble, we will be able to assign a vector on the Bloch sphere. So then imagine we have two types of ensembles of two-level systems. We have an ensemble of two-level systems where vectors all lie on this plane in the middle of the sphere, and they roughly pointing in the same direction. Or we have an ensemble of two-level systems where each two-level system is characterized by a wave function. The wave function is characterized by a vector. Again, each of the vectors lies in the plane in the middle of the sphere, but they are equally distributed over the whole plane. So then let's now try to calculate elements of density matrix for this and this case. Well, not calculate, but at least tries to estimate them. So if all the vectors in this case lie in the plane just in the middle of the sphere, so that if you try to calculate C1, in this case you can see the C1 is proportional to theta divided by 2, then theta in this case is 90 degrees, so it would be cosinus 45 degrees, and we take it in square, it would be 1 over 2. And here in case of C2, again theta is 90 degrees, we put here 90 degrees, divided by 2 it's 45, sinus 45 degrees, again taken in square, it's again 1 over 2. So basically, if the vector is somewhere in this plane, which separates two halves of the Bloch sphere, then we can say that this situation corresponds to the case when the probability to find electron in the ground in the excited state is exactly 50%. Here we will have the very same situation. Basically, for each of these vectors, we are pointing somewhere in the arbitrary direction in the plane. We will be able to calculate this product of density matrix, and if you calculate this for each of these vectors, we will say for every of these vectors, C1 star times C1 would be exactly 1 over 2. That's why averaging over the whole ensemble will give me 1 over 2. And here, for the probability to find electron in the excited state, or for diagonal components of the density matrix ρ 2, 2, you will also find 1 over 2. So basically, if you look simply at the diagonal components of the density matrix, you will not see any difference between this case and this case. But let's now look at the off-diagonal components. If you look at the off-diagonal components and try to write the expression for C2 star C1 and averaged over the whole ensemble, here, since we roughly assume that all these vectors approximately pointing in the same direction, so then it means that if you take averaging over the whole ensemble, you will get approximately 1 over 2, then this exponential function with coefficient phi, which basically describes us this angle between all these vectors and x-axis. So basically, if here we define x-axis in the direction pointing in this direction, in the direction pointing in the direction of x-axis here, then phi would be 90%, 90 degrees, for instance. But then also time dependence would be given by, so here it should be additional t and parentheses, and then also between parentheses, of course. then what we can observe here is also explicit time dependence, which shows us oscillations of this quantity at the frequency which corresponds to the energy difference between the ground and the excited state. Then let's look now at the different situation, at this situation where we have Bloch at each of the vectors on the Bloch sphere for the ensemble of for each of the two-level systems, and the ensemble is pointing in a arbitrary direction, such that if you try to find an averaging, an average quantity C2 star C1, since each of these vectors will have its own phase phi, what we will calculate at the end, it would be 0. So basically, if we now summarize these two situations, then we have the same element rho 1 1, which basically tells us something about probability to find electron in the ground state. The same quantity for the density for another diagonal element of the ground of the density matrix rho 2 2, which tells us about the probability to find electron in the excited state. Then we'll have time dependence. So here again I lost t and one parenthesis in this expression. So this then we have in this case element rho 1 2, which oscillates in time, and in this case rho 1 2 is equal to 0. So and this makes big difference between this case and this case, and especially because if you now refer to the things I told at the very beginning of the lecture, that element rho 1 2, this off-diagonal elements of the density matrix, is related to the polarization of the ensemble of two-level systems. So that basically means that here in this case polarization is not equal to 0, and in this case polarization of the ensemble of two-level systems is equal to 0. Well, polarization, if you remember now the wave equation which we derived at the very first lecture, if polarization of whatever medium, whatever substance is not equal to 0 and it oscillates in time, it becomes a source of light. So basically ensemble of two-level systems which described by this set of Bloch, by this set of vectors on Bloch sphere will emit light, and ensemble of two-level systems which described by the ensemble of two-level systems with wave functions which are described by these vectors on the Bloch sphere will have 0 net polarization, and it means this ensemble will not emit light. In this respect, it is very interesting now to look at the following situation. Then here on this slide I will try to explain you a phenomenon which is called spin echo. So imagine we have an ensemble of two-level systems. And why people call it spin echo? Because ensemble of two-level systems corresponds to two states. So that's ensemble of two levels. In the ensemble of two-level system, every particular two-level system corresponds to a state, to two states, where ground state is state spin up and the excited state is state spin down. So there's something which is the transition between these two states would be called, for instance, nuclear magnetic resonance in physics. So we imagine that we measure nuclear magnetic resonance. So we have ensemble of two-level systems. Physically it means that the ground state corresponds to state of electron with spin up, and the excited state corresponds to state of the electron with state down, then with spin state down. Then for each of these two-level systems we assign wave function. And the wave function will have, as we discussed already, two coefficients, C1t and C2t. Then what we do now, we introduce slight inequivalence between these two-level systems. What we introduce is a slight energy difference between each individual, between each two-level systems. So for instance, if this two-level system has the smallest energy, the next two-level system has slightly higher energy, and the third system has even more higher energy. and so on and so forth. So basically it would be called in physics inhomogeneous ensemble of two-level systems. Yeah? So basically each of the two-level systems has its own energy. So imagine we have been able to realize this ensemble of two-level systems, introducing, for instance, gradient magnetic field in the sample, or introducing magnetic field which was not perfectly homogeneous. So it means that the splitting between the states, spin up and spin down, would be not homogeneous over the whole sample. And have situation like this. Now, imagine that we excite system. So the system was first, all the spins, all the electrons were in the state spin up, in the ground state. Now we excite the ensemble of two-level systems such that we create, for every of two-level systems, we create superposition of state 1 and state 2. So on the Bloch sphere, it would correspond to a rotation of all vectors which we assign to wave functions of two-level systems. We rotate all these vectors over 90 degrees. Then, in the following time domain, we let two-level systems evolve in time. They will evolve in time, and this evolution in time will be practically expressed by building up an sort of umbrella here of this of all these vectors. Why? Because each of the two-level systems has its own frequency, so they will not oscillate all together, but slowly in time they will accumulate phase difference. So basically, accumulation of the phase difference between all these two-level systems will be equivalent to opening up this umbrella type structure of arrows of the vectors. But now imagine that we waited for the moment until we got the largest opening of all these vectors, and then we give another pulse of magnetic field, and this pulse of magnetic field changes the phase of each of the individual two levels. In each of individual two-level systems, this magnetic field pulse changes the phase of the wave functions of 180 degrees here. So basically it means that we rotate all the vectors over 180 degrees and we let them again evolve all together. We let them evolve until at the moment, which was actually at the time after time period, which was equal which was equal to the time period between point B and point C. Here, if you wait this period of time between point E and point F, at the point F, all these vectors will eventually come together, and as I showed you, when they all come together, if you talk about ensemble of two-level systems and calculate the polarization, but in this particular case you have to calculate the magnetization, it's not so much difference. So but then if they all come together, and imagine each of these two-level systems is associated with electric dipole, it will be net polarization induced. So in this particular case, since we talk about spin up and spin down, it will be net magnetization, but it doesn't matter at the end. And then suddenly all these two-level systems will acquire the same phase, and suddenly there will be net magnetization induced in the medium. And you can check if in the wave equation, if the net magnetization is induced in the medium or net polarization is induced in the medium. In each of these cases, according to the wave equation, medium should become the source of light. So basically what we should observe experimentally is that we give one pulse, which is called 90-degree pulse. Then we wait a little bit, then we give another pulse, which is called 180 degrees pulse. And exactly after the period, after time which separates 90-degree pulse and 180-degree pulse, what we should observe exactly after these periods is that the sample becomes a source of light. So basically, sample re-emit a pulse of electromagnetic radiation, and this pulse is called an echo. So this phenomenon was discovered when people were studying nuclear magnetic resonance in I don't remember exactly when it happened, in 60s, and then they published this paper in Physics Today, and there was a nice picture which was used to explain this phenomenon. That imagine that we have athletic stadium, and in the competition, then we give the signal and all runners start to run, and at a certain time each of the runner is on the since they have all different conditions, they will be spread over the whole stadium. And then imagine at a certain moment we give another signal and we'll let these runners run in the opposite direction. And if we assume that the speed of the runners doesn't change over time, if these runners are experienced ones, then exactly at the time period that separates first and the second signal, if you wait exactly the same period of time after the second signal, we should see all runners coming together through the start line. So basically, when all runners come together, in physics it would correspond to a situation when light starts to emit light. So it would be an effect of echo. So something similar you can also observe in visible spectral range. As I said, the only difference would be that instead of spin up and spin down, the interpretation of two-level system would be different. It will be just two-level system. For the transition, you will be able to assign dipole moment, and instead of induced magnetization and echo induced due to time-dependent magnetization, you will be echo induced due to time-dependent polarization. Well, let me summarize at this point. So the Bloch sphere provides a possibility to describe the wave function of an electron in two-level system in an intuitive way. Using the concept of the Bloch sphere, we can illustrate and intuitively understand behavior of ensemble of two-level systems. An ensemble of two-level systems can show up effects of echo. So basically, effects of echo would be like if you give one pulse, second pulse, wait exactly the time that separates second and the first pulse, and then after this time, sample will suddenly emit a pulse of light. So it would be called echo, and depending on the nature of the two-level systems, you would be able to talk about in this case either about spin echo or photon echo. And this I would like to conclude this lecture. Thank you very much.